Hi Math 281 students, this is Scott, and I hope I have all of your names down now. I'm going to give it a quick try. Let's see, Mercy, Mydoris, Araceli, Michelle, Melanie, Tabat, Leticia, Annalise, and Anthony, George, Horacio, and Saul. I hope I said everybody's name. If I didn't, I feel really bad right now. Anyway, I hope I've got all your names right. I hope you guys are doing well, and I hope you don't mind. I'm going to do a quick wrap-up of what I was presenting today in class. Unlike most classes where I could just come in the next period and finish up what I was doing before, we have a pretty tight schedule since we only meet one time per week. And so I don't want to hold us back, and I hope you guys would not mind just watching a short video. Just want to wrap up that problem I was showing you about stars in class today, which is Monday, February 2nd, and then show you one more problem that is about distance and rate and time calculations, which I promise is a short problem. So this won't take very long. I've drawn a whole bunch of these stars on the board again. We had drawn a lot of these already today, this morning. And going back to Poya's four-step problem-solving method, we were looking for patterns, and we were trying to solve smaller versions of the 1,000 pointed star problem. So we looked for stars with 5, 6, 7, 8, 9, 10, 11, and 12 points. So I've drawn them here, and we talked about that idea that when we're drawing these segments of the star, we're sort of skipping points. We're skipping over points, and we're always skipping over the same number of points. And what we did is we introduced this, this kind of parameter j, which measures how often we connect the points. So like here's a n equals 9 case. If j equals 2, it means we connect every 2 points. Every second point as we draw the points around a circle, right? And we get this beautiful star. And we also could draw the star that's over here where j is 4. So now we're skipping every 4 points as we go around the outside of the figure. But, the question becomes, well, which values of j can you use? And, we had said in class that we know that we cannot use j equal to 1, because if we connect every point, we're just going to end up with a n-gon. We're not going to get a star. We're not going to have crossing segments, right? So j cannot be 1. And if we go the opposite direction around the circle, then we also can't use n minus 1, because that's basically connecting this. That's the same figure, just in the opposite orientation. So we take those two values out for whatever n is. Okay? So, if you're talking about a 1,000 pointed star, then we're saying that j does not equal 1 and j does not equal 999. Okay? So we do that. The other thing we hopefully notice today is that j cannot be any number that somehow divides into the n value. So, or even has any common factors with it. So like here, notice that 2 and 7 and 4 and 5, those are all safe. They have no common factors with 9. But the numbers 3 and 6 do have common factors with 9. And if you try to draw stars using j equal to 3 or 6, what happens is you create premature triangles, actually. You'll return back to the starting point before you've connected up the entire star. And that's a violation of the rules for a star. So the question really becomes, how many of the possible j values don't have any common factors with n? Okay, so if we look at 1,000 really quickly, if you think about it, so it becomes a little bit of a number theory kind of question, right? So if you think about the number 1,000, what we have to look at is, well, which numbers would not share any of the factors that are in 1,000. Of course, 1,000 is, you can break it down in terms of prime. It's really 10 cubed, right? 10 times 10 times 10. And that means that there's 3 factors of 2 and 3 factors of 5, right? So any value of j that is made out of 2's and 5's is not going to work here, right? So in particular, all of the even values of j have to be thrown away, right? So we throw away the even values of j so I guess the values of j that we are thinking about are the values that go all the way, well, let's just go all the way to 1,000, right? Okay, so we'll take that. So that's 1,000 numbers. But what I'm going to do is I'm going to throw away all of the even values of j that are up there, including the last one. We really can't use 1,000 anyway. So I'm going to throw away all of those even numbers. There's 500 odd numbers in this list, okay? Some of those odd numbers are also going to be a problem, right? Any number that has a 5 in it as a factor will be a value of j that we cannot use. And that would actually be sort of every fifth number, right? So every fifth number. So if we're thinking about 1,000 numbers in total, and there are 1/5 of those that will have factors of 5 in them, then we have to subtract 200 numbers, right, from the list. So we started with all 1,000 numbers as possible values for j. But then we took out all of the even ones and all of the multiples of 5. But you know what we just did by mistake, sort of? We subtracted those numbers that are multiples of 10 twice. Because if you're a multiple of 10, you are even, so you're subtracted here. But you're also a multiple of 5, so you got subtracted here too. So what mathematicians do is they correct their mistake. If they subtracted something twice, they put it back in once. And what we're going to put back in here are the multiples of 10. Well, that would be 10, 20, 30, 40, 50, and so on, all the way up to 1,000. And there are exactly 100 of those. Every 10th number in that list of 1,000 numbers must be restored to our total. Okay. So if we work this out, this actually comes out to 400. Okay, so this comes out to 400 values here. And as it turns out, these two numbers, 1 and 999, are in this list of 400 numbers. So what you have to do next is subtract those out. So there are 398 j values. So is that the answer, though? The problem is, it's almost right. The problem is, as we see in these examples, all of these examples here, there are always two different j values that make the same star, right? So for every 2 j values, we only get 1 star. So if I have 398 j values, right, I have to divide that by 2, which gives me 199 stars. And that is actually the answer to the question. 199 stars. Okay. So a little bit involved, right? There's a lot of problem solving here. There's a lot of looking for patterns. This idea of the j values is something that you're not going to think of in the first second that you look at the problem. You have to spend some time. You have to draw some simpler examples. You have to talk to a friend. You have to do all of those suggestions about how to devise and carry out a plan that we talked about earlier. Once you realize that you're really counting the j values, then it becomes a little bit more of a numerical problem. But, okay, so I wanted to show that to you. Now, give me just a second. I'm going to move the camera over to the other board where I've put another problem on the board that I'd like to solve with you. Okay, so here we go. I love having all this space down here to write on the boards. Okay, here it is. Okay, now if you can't read that whole thing, it's kind of a long question. Don't worry about it too much. If you go to the website where the PowerPoint lesson for this class meeting today is posted. On the very last slide of the PowerPoint presentation, you'll find this question typed out very nicely. So you can look at it there, but I wanted to write it on the board so we could kind of read it together. Okay, so let's read this question. Ed and Sue bike at equal and constant rates. Similarly, they jog at equal and constant rates, and they swim at equal and constant rates. Now remember, the first step of Poya's four-step problem-solving method is to make sure we understand the question. So as we're going along here, there's a lot of words. It's not a bad idea to stop and pause and make sure we understand what we're saying. So we have these two people, Ed and Sue, and they do three things, right? They bike, they jog, and they swim. And Ed and Sue are equally fast at all three of those things, right? Equal and constant rates. So they're equally fast and they stay at the same constant rate all of the time. Okay? So, in fact, what we might do before I even go any further, and this is one of the things that will help us understand the problem, is although there maybe isn't any picture that I would draw, I would certainly start thinking about notation. So I might use something like a B to equal the biking rate. I'm establishing some variables here, okay? And you don't have to use these letters, of course, but this is just one idea. I'm going to use a J to denote the jogging rate. And then I'm going to use an S to denote the swimming rate. And I don't have to say whether I'm talking about Ed's rate or Sue's rate because they're equal. They're both the same, right? In fact, in some ways, we don't really need two people here. Just one person is enough. They have a biking rate, a jogging rate, and a swimming rate. And these are all constant numbers, okay? So that's what the first part of the question says. Now, here's the next part. Ed covers 74 kilometers if he bikes for 2 hours, jogs for 3 hours, and swims for 4 hours. While Sue covers 91 kilometers if she jogs for 2 hours, swims for 3 hours, and bikes for 4 hours. So let's stop and think about that for a moment. Okay, so this is where the whole distance equals rate times time comes into play. So we know what the rates are of these two people in biking, jogging, and swimming. And if we take those rates and multiply them by the time, we'll figure out the distance. Okay, so for example, if Ed has biked for 2 hours, then how far did he go on his bicycle if B is his biking rate? Well, the answer is 2 times B, right? So if he's biking at 10 kilometers an hour and he does it for 2 hours, well, that would be 20 kilometers that he's covered. So you multiply the rate times the time, okay? But we're adding because we're sort of totaling up Ed's total distance. So he biked for 2 hours, then he jogged for 3 hours, so I'm going to write that as 3J. And then we add to that the fact that he swam for 4 hours. And that all adds up to 74 kilometers, okay? Now with Sue, we can set up another equation. She covers 91 kilometers, but her equation is a little bit different. So I want to put these parameters in the same order. So she biked for 4 hours, so 4B. She jogged for 2 hours, that's 2J. And then she swam for 3 hours, so that's 3S. That one adds up to 91. Okay? We're most of the way through the question. Hopefully you understand so far what's going on. Okay? Nice thing about a video, it's not all clear. You can always back it up a little bit and just check it out one more time. But these are the two equations that I'm getting from the words kind of in the middle of the text of the question. All right? Let's go on with the rest of the question now. Their biking, jogging, and swimming rates are whole numbers of kilometers per hour. So that just means that B, J, and S are whole numbers. Okay? That's going to be important, actually. And the final question then says, find the sum of the squares of Ed's biking, jogging, and swimming rates. Well, What is that? The sum of the squares. So that means I have to square each of these three rates and add them up. Right? So in other words, it's never a bad idea to write down what it is that we are trying to do here. So what we want to find is b squared plus j squared plus s squared, right? Those sums of the squares of those three rates. So, you probably remember from high school algebra that if you have sort of two equations and two unknowns, you can sort of plug one of them into the other and solve for the values. This is a little tricky because there's only two equations, but we have three unknowns. Okay? But maybe what we could try and think about doing, and this is sort of the devising the plan part, assuming that we sort of at this point we understand the question. Okay. One plan would be to try to at least eliminate one of the variables, because we have three of them here. Maybe we could reduce to a simpler equation that only has two of the variables. For example, there's many ways to accomplish that, but I'll just show you one that kind of sticks out in my mind. If I look at the first equation, and if I thought about doubling it, just put a factor of 2 into every single part of it, I'll have 4b on the first equation and also on the second equation. And at that point, I would be able to subtract. And by subtracting, I would get rid of the b altogether. So that's actually what I'm going to do. I'm going to, let me write it right above the top line. I'm going to double the first equation. So 4b plus 6j plus 8s equals, if I double 74, I'm going to get 148. I'm going to kind of ignore the equation that I just started with and just write down the new one. And now I'm going to just subtract these equations. See, because 4b minus 4b is 0. Yeah? 6j minus 2j is 4j. And 8s minus 3s is 5s. I'm just kind of doing like a vertical subtraction. On the right side, I have 148, and I'm going to subtract 91. That's going to give me 57, right? So we have this equation right here. All right. Remember now, okay, so this is an equation. If you thought about it in terms of high school algebra, you would say, well, this is a line that has infinitely many points on it. Tons of values of j, tons of values of s, and so on. Okay, you could actually solve this equation almost like it was in the form of y equals mx plus b. It's different letters here. We have j and s instead of y and x, but it's the same idea, right? It's an equation of a line. But the thing we have going for us here is that we are told, let's go back, that these numbers, the j and the s and the b, they are all whole numbers. They have to be whole numbers. No fractions. Okay? The other thing is they're not going to be negative numbers either. They're not going to be negative. So that's going to actually limit, I'm going to go ahead and erase part of the question here. That's going to limit the possibilities. So, for example, if I tried to say, suppose that j is equal to 0, is that a possibility? From this equation, if j is 0, look what happens to s. S would then have to be 57 divided by 5, which is not a whole number, right? That's a fraction that has a remainder. When you divide 57 by 5, you do not get an integer. So this is impossible. I'll just put an x there, right? S is not a whole number. Okay? And what we're going to find pretty quickly is that there are a lot of values of j for which that problem happens. So if j is equal to 1, right? Well, then I have a 4 here, which I can subtract to the other side, but I get 5s equals 53. Same problem, right? Still not going to work for the same reason, okay? And you can keep going like this. If j is equal to 2, let's see, if j is equal to 2, this is 8. If I subtract 8 to the other side from 57, I get 49. 5 does not go into 49, so that's not going to give you a whole number for s either. Okay, how about j equals 3? Well, this is an interesting one, because 4 times 3 is 12. And if I subtract 12 into 57, I actually get 45. And if that is the case, then I can actually choose s to be equal to 9. Ah, well, that looks pretty promising. So does that have to be the answer, though? Could there be another answer? Well, maybe to help you think about that, look what happens. Okay, there's obviously other values we could try. If we tried 13 for j, I'm just going to skip ahead. Don't want to make it watch this for too much longer. If j is 13, we're going to get right here, we're going to get 52. 4 times 13 is 52. And if I subtract 52 into 57, I get 5, which means s equals 1 would work. It makes us start to wonder if there's only one answer to this problem. Okay, so this seems to be okay. Most of the values of j are not going to work, but here's another one that works, and there's actually a third one, which is right in the middle, actually. If j is equal to 8, then we have 32 right here. 57 minus 32 is 25, and s equals 5 would give us a solution. Okay. And I'm going to tell you that those are the only ones that work. I mean, if you let j get any bigger than 14 or 15, what's going to happen is you're going to start getting negative numbers for s in order to make this work. And we know that that cannot be true. Okay, so to keep both variables positive, we're kind of limited on what the range of values for j and s could be. Okay, but are all three of these allowed? Well, the answer is only one of them is right. So if you want to think about it for a minute, you can pause the video and stop and think, why did I get 3 possibilities here, and why is there only one of them that's right? So you can pause and think about it if you want. I'm going to go ahead and tell you why, okay, for those of you who don't like the suspense. Remember that we have another variable, which is b. And b also has to be a whole number. If we look at, it doesn't matter which equation, let's take a look at this equation right here. 4b plus 2j plus 3s equals 91. If I put in, let's just do the first one. If I put in 3 for j and 9 for s, let's see, what am I going to get? Let's write this equation again here. If I put in 3 for j and 9 for s, let's do a little mental math. I have 91, and I'm going to take these numbers and move them to the other side. So 91 minus 27. And if I subtract 27 here, I'm going to get 64. And if I subtract another 6, because 2 times j will be 6, that brings me down to 58. And you know what? 58 is not a multiple of 4. So b is not a whole number in this case. And it turns out it's not a whole number in the last case either. The only case where it works is right here. When j is 8, let's just do the calculation. When j is 8 and s is 5, I've got 16 and 15, which makes 31 when I add them together. And if I subtract that from 91, I get 60. And 60 goes into 4 exactly 15 times. So b would be 15. So here is the solution that works. b is 15. I'm going to come back now and do my final calculation. 15, I have to square that. j was 8, I have to square that. And s was 5, and I have to square that. And if you work that out, it comes out to 314. Okay? So, it took us a little while to understand the problem. Then we had to devise a plan, and that involved sort of setting up notation, equations, and this idea of subtracting equations to get a simpler one. Okay? And then we just had to do kind of a list. The idea was, we know that this is not a really long problem because J and S have to be positive, and everything is sort of relatively small, right? 57 isn't that big. So the number of choices for J and S that's going to work here is pretty limited, okay? So we can just make a list, and we find that there's sort of 3 final candidates that are possible in this scenario. And only one of those 3, when I go back to the equation with B in it, only one of these 3 choices of J and S gives us a value of B that works. All right? So then we can plug in the numbers and get the answer. Okay, so what I just did for you right there was look back. Remember, the 4th part of Poya's problem-solving strategy is to look back at what you did and make sure that it's reasonable, that it makes sense. So anyway, I have really enjoyed not only class today, but also the chance to follow up with you here. I appreciate your time to watch this. If anything is still not clear, obviously you can rewind this segment a little bit if you want, or you can come talk to me or Angel or one another. We want to really encourage you guys that one of the things that's important in this class is open communication, right? We're doing this because we want to do it. We enjoy working with you all, and would love to talk with you more. If you have any questions on the homework that I've asked you to do for next Monday, again, feel free to talk to me or Angel or others in the class, and I look forward to seeing you very soon. Okay, thank you and have a good day.